All right, let's see if we can develop a theory for flux through spheres. I bet we can totally do this. So the goal, right, is to figure out another one of these D area things with a vector hat, right? Yes?
Sure. Yeah.
Okay, so I should remember that these are a normal vector and a regular D area. Okay, so this is going to be a story about a sphere with a radius of r. Maybe we should come on to a kind of random point here. All right, sphere, radius r. If I had a little patch of area on this thing, how big would that little patch of area on this thing be?
Delta V.
Okay, so that's a good thought. So I'm looking for delta area, right? I'm thinking, okay, this is maybe more or less delta what, delta what?
So it's rho delta. We're doing the rho thing on it.
Yeah, we're gonna do a row thing, so there's gonna be a row.
Delta phi, delta theta.
Ah, good. And there's going to be a delta theta and a delta phi, right? Because those are really the only things that matter here, right? You guys see that? The rho is going to be fixed, right? So I probably shouldn't call it rho, I should call it r. And then what's the formula for the area of a patch? We actually developed this a while ago.
Yeah.
Wasn't it rho squared? Something else.
Rho squared sine.
Yeah, it's rho squared sine phi. And then normally here we'd have a d rho, right? But that's just changing the depth. All I want is the patch, so I don't need that third dimension, right? So you guys see that? Because I'm looking for a change in area. So there's my change in area. What else do I need?
Oh, the normal vector?
Yeah, I need a normal vector, right? Okay, so what are the coordinates of a point out here on a sphere? This is probably going to be the hardest question I ask you all semester.
Because we already have the answer somewhere else in our notes.
Because you already have the answer, you should know.
X, Y, Z.
Okay.
The spherical relation of x, y, and z.
Exactly. The spherical relation of x, y, and z, which is, I'm just going to keep moving these commas until you guys figure it out.
Until they just over on that board.
Rho sine phi cosine theta. Rho sine phi sine theta. Or R.
And then
R
this.
cosine phi.
Oops, what did I do? I think it's
Sine.
sine. And r
Sine, cosine, then sine, sine, then just cosine.
cosine phi. Okay, cool, yes? Now, what's a vector that sticks straight out of the sphere at the end of that thing, right? So that was this vector here. Now, what's a vector that sticks straight out of that?
Everything with ij. Same thing to 0.
And that thing, right? You guys see that? This vector points straight out at the surface anyway. So of course if I continue along it a little bit, right, it still sticks straight out. You guys see that? That was actually easier than cylindrical, because on cylindrical I had to worry about z's and how that didn't matter. Here, hey, this thing. But what does the normal vector need to be?
One vector.
It needs to be one long, right? How long is this thing? R. So if I want to make this one long, what do I need to do?
Divide by R.
Slash e the r's out of it, right? So that means that n is sine phi cosine theta, sine phi sine theta, and cosine phi. So what's your D area thing now? Here's your take home, right?
Sine, phi.
Just dot product data.
Yeah, it's a whole mess, right? It's
Yeah.
this whole normal vector and that whole delta area thing. So you got the vector sine phi cosine theta, comma sine phi sine theta,
Bunch of grossness.
comma cosine phi multiplied by r squared sine phi d
Theta d phi.
d theta d phi. Perfect. And this seems like really horrible, right? And it kind of is, except that we know all these things, right?
Yeah.
That's x, that's y, that's z out of spherical, right? That's the chunk of d volume out of spherical, right? That's d volume divided by d rho. Cool.
Those X, Y, and Z are X, Y.
Yeah, and these
or
x's, y's, and z's are over r, or over rho, rather. And then this is replace rho squared with r squared. Cool. So although it's a little bit annoying, right? The roots of it are in something we know pretty well. Cool.